Video presentation of our group's course project for the University of Georgia's optics course. This course was instructed by Professor Yuping Zhao in the fall of 2023. For our experiment, we wanted to see if image analysis could be used to determine whether milk is curdled or not. Milk curdling occurs when it's exposed to bacteria, enzymes, or acids. Curds form by proteins in the milk coagulating together into larger structures, and knowing if curds are present in milk is crucial for quality control in the dairy industry. If curds are present when they are not expected, it can be a sign of unwanted bacteria. However, this knowledge can also be useful in the creation of cheese or other dairy-based products. The main theory behind our analysis was the Fourier transform of an image. A Fourier transform is a mathematical operation that breaks down a function or a signal into its constituent frequencies. In this context, the signal was an image of milk. Here's an example of images and their Fourier transforms. In the image on the right, you can see lines in the brick occurring at steady spatial frequencies. This translates to the Fourier transform having more information in the vertical and horizontal axes. So for uncurdled milk, the substance is homogeneous and thus has little to no spatial frequencies, so we expected the Fourier transform to be a single point. Curdled milk is a heterogeneous substance. Because the curds occur at random locations in the image, the spatial frequencies that occur are in all directions. Due to this, we still expected a point at the center. However, that point would be less intense and have a much wider radius. Images of milk were captured by putting a milk solution in an apparatus and shining a laser through the apparatus. And the apparatus would be placed at location M, shown in the diagram. It's a similar optical setup to the one used in our experiment, but it's simplified. The bottom diagram shows how curdled milk, or M in this case, would perturb the light rays, and we captured these Fourier transforms using our smartphone cameras.
The first thing we have is the helium neon gas lamp. That's where our laser, we called it a lamp, doesn't matter.
Laser lamp.
Right. Bounces off the mirror towards the second mirror right here. It's then partially obstructed by the iris to narrow the beam. Passes through a lens that expands it towards the second iris, which further obstructs the beam. And then it passes through our sample through a second lens that stops the diversion. Another lens that converges it.
Well, that does the actual
Second lens.
transform, magnifies the transform, and then where the trans. Alright, so just showing that we're taking off a mesh and using an actual cuvette. The sample would normally be, obviously this is just water. Allow it to actually go through the beam, and showing that
To curdle the milk, we used a citric acid solution. Comparing milk with no citric acid nor curds to milk with curds and citric acid, you can see the intensity profiles of the Fourier transforms have different widths. We noticed that as the citric acid solution decreased in concentration, the curds became smaller and the beam widths became larger, indicating more spatial frequencies in images with smaller curds. We also noticed that milk stopped curdling when the solution reached a concentration lower than 0.1056 milligrams per milliliter. To obtain the widths of the central maximum of the transforms, we fitted the intensity profiles to a Gaussian distribution. Here are the results for uncurdled milk, and you can see the width here. And here is curdled milk. And here is curdled milk with a less intense citric acid solution. And even less intense with an even larger beam width. And finally, the milk stopped curdling when it reached this concentration of citric acid. Plotting the concentrations versus beam widths shows the citric acid solution must reach a threshold concentration before the milk starts curdling. As the citric acid solution became stronger, we could visually see the curds becoming larger and the beam width size decreasing. There is a clear correlation between the beam width and curd size. Our group just does not have the math to explain any of it yet. So future work following this experiment could correlate the beam width with the curd size, making this image analysis technique even more applicable to the dairy industry.